So let's talk about the rules. So the first rule is the oxidation number of an atom in its elemental form, okay? So in its elemental form is always 0. So take for example iron, oxidation number out here is going to be 0, okay? What about nitrogen? Nitrogen is a diatomic molecule. That's the elemental form. Again, oxidation number is going to be 0, okay? The second rule, oxidation number of a monoatomic ion is the same as its charge. So, oxidation number of sodium plus, which is a monoatomic ion, would be equal to 1 plus, same as its charge. How about calcium? The calcium ion, the oxidation number would be equal to plus 2. Okay. Now let me make some clarifications out here. Okay. Notice carefully, in the ionic form, the coefficient of the charge is always sitting to the left of the charge. Okay, it's always to the left. So you write the coefficient first, denoting how many charges, and then the plus. But the oxidation number is always going to be the charge first and then the number. Okay, keep that in mind. Okay, so, and I'll create a little column out here, oxidation number, and out here this is the ion. Okay, so it's important to understand the numbers on the right hand side when you write the oxidation number. Okay, let's take a look at the third rule. In a neutral molecule, the oxidation number, the sum of all oxidation numbers, so that means of all the atoms constituting the neutral molecule, is always equal to 0. Okay, so let's take for example, HCl. So in HCl, remember we said that you have to assume that the chlorine is pulling all the electrons to itself because it's the more electronegative atom. So that would be H plus and Cl minus. Okay, so the oxidation number of H is going to be plus 1, and the oxidation number of Cl is going to be minus 1. If you take plus 1 and minus 1, so you're adding those together, you will get 0. So that is what happens in a neutral molecule. Okay. Now, by the same logic, if you have an ion, like a polyatomic ion, okay, so I'm going to do polyatomic ion. The oxidation number, the sum of all the oxidation numbers should equal the charge on the ion. Okay, so sum of, I'm going to just go ahead and erase this out here so I can create some space. Sum of oxidation numbers should equal the charge on the ion. Okay, so for example, if I have NO3 minus, if I add up all the oxidation numbers for the 3 oxygens and 1 nitrogen, that should equal a charge of minus 1. Notice carefully, that's a 1 minus, but the oxidation number is minus 1. Okay, so that is the oxidation number of this species. Okay, another example would be CO3 2 minus. Guess what the oxidation number is going to be? It's going to be minus 2. All right, the fourth rule is going to be all metals have an oxidation number equal to their charge. Okay, so all metals have an oxidation number equal to their charge. So if I'm looking at Fe3 plus, all that metal, look at the charge, it's got a 3 plus, so therefore the oxidation number is going to be plus 3, okay, for that species. Likewise, if I have something like potassium chloride, and by the way, this Fe3 plus, I just wrote the ion, it really could exist in a compound like this, FeCl3, okay? So then if you split this into ions, it would be the Fe3 plus and 3Cl minus. So that's the metal. What's the oxidation number? Plus 3. So therefore, you would actually write that oxidation number like this, plus 3, right above the Fe, okay? Same thing with the KCl. KCl would be split, if you split this into its ions, it would be, it would be K plus and Cl minus, okay? And the oxidation number of K, same as the charge on the ion, but only thing we write it as plus 1. All right, I hope that made sense. Now the next rule is going to be, let's call that rule number 5, is going to be how do you assign oxidation numbers for non-metals, okay? So there's a priority sequence for non-metals. Non-metal, let's call it non-metal oxidation numbers, okay? I'm going to try to fit it in here, but then it might just bleed over there, okay? So if I write, I'll write the non-metal out here, and then I'll write oxidation number out here, okay? So at the top of the list is fluorine, and fluorine has an oxidation number of -1, okay? Then comes hydrogen. Hydrogen is +1. Then comes oxygen. Oxygen is -2, okay? After oxygen comes the halogens. Halogens are group 7A, okay? Those would be -1, and then you have the oxygen group. So everything in group 6A is going to be -2, and then finally you have the nitrogen group, which is group 5A, which would be -3, okay? And by the way, this priority is whatever's higher takes priority, okay? So when you assign oxidation numbers, if it's higher up in the group, that's the one that's going to take priority. So higher, and we'll take a look at a few examples to kind of help us understand this. Higher gets, or higher gets priority. So you might want to write down these rules and take down this table, because we're going to use this for solving some problems. So you might have so you should have a ready reference, okay, while you're doing this. So I'm going to go ahead and write down the next rule, and I'm going to erase this table. So rule number 6 out here is going to be the oxidation number of elements in a compound they always depend on what other elements are present. And there's only 2 exceptions to this rule. The exceptions are group 1A, elements. So group 1A are basically your lithium, sodium, potassium, and so on. They always have a charge, have an oxidation number of +1. Okay, and then group 2A, let me write these 1A and 2A a little bit differently. 1A and 2A. 2A is always going to be +2. So these two are standard, okay? So anything in group 1A or 2A is always going to be +1 or +2. Everything else can change depending upon what else is present. So let's take a look at this example. Let's say we're trying to assign oxidation numbers to this compound. as you can see, sodium actually is in group 1A, so that's not an exception to the rule. So I'm going to use a different color out here. So sodium is actually +1 because it's in 1A. And then this oxygen, do not assume that it's -2 based on the previous set of rules, okay? Because if you recall, one of the initial rules was that all the oxidation numbers of all the atoms in a neutral compound, which this is, always need to add up to 0, okay? So the only one we have to figure out is oxygen out here. Do not assume it's -2. So we're going to call this X. So the simplest way to go about this is to write an equation in X. So we have +1 plus X, but see, there's 2 sodiums, right? So we're going to multiply that by 2, and there's 2 oxygens. So we're going to multiply the X with 2, so let's rewrite that a little differently. So that's 2X, and that equals to 0, because that's the net charge of the molecule. So that gives me 2 plus 2X is equal to 0, or 2X is equal to -2, or X is equal to -1. Look at that. So that oxygen actually has a -1 oxidation state, not -2 as the table predicted, okay? And so those rules that I wrote down, the rules themselves are in priority, not just the ones at the table, but whatever's above actually takes priority over what's below, okay? So this is one example, okay? Now, take a look at another scenario where, let's say you have H2O, very simple molecule, water. Now, in H2O, turns out hydrogen, if you recall from the little table I drew, hydrogen was higher than oxygen, okay? So hydrogen actually is assigned an oxidation state of +1. And oxygen, again, don't assume, so we're going to call that X, okay? So let's go ahead and write a equation in X and solve, because the total should equal to 0. So that's going to be 2 times +1 plus X is equal to 0. Because there's only one oxygen, so X shows up only once, okay? So that's going to be 2 plus X is equal to 0. So X is equal to -2. And that actually ends up being the same as what shows up on the table. So this is the normal oxidation state of oxygen. You'll typically see this a lot of times. And then sometimes you'll see changing, okay? So don't be surprised if it changes. But just understand this, if you follow the rules sequentially, you should be fine. And the way to get good at this is to just practice, okay? So we need to keep in mind that whenever we're taking a look and trying to figure out the oxidation state or the oxidation number of an element, once we follow the rules, you will come across elements such as carbon, for example, which doesn't fall in any of those rules. It's not in the table at all, okay? And it's not in any of the rules that I specified. So what should you do? Well, the simplest way is assign an oxidation number of X for whichever element you're trying to determine, and then add all the oxidation numbers together with X, set up an equation in X, and then solve for X, okay? So take a look at carbon dioxide. So we know that oxygen is going to be -2 from the table, but we don't know carbon, okay? So we're going to call that X, and then we're going to set up an equation in X and solve for X. So I'm going to write that out here. So X plus, there are 2 oxygens, so 2 times -2 is equal to 0, because the total charge on carbon dioxide is 0. So X minus 4 is equal to 0, or X is equal to 4. To be precise, that's +4, right? So the oxidation number of carbon in carbon dioxide is +4.